Some of the most powerful technologies we know don't look like machines. They're not built in factories. They're pulled from the ground. From climate change to clean energy, from quantum memory to invisible electronics, the answers may not lie in what we invent, but what we overlooked. These 10 minerals aren't priceless because they're beautiful. They're valuable because they do what nothing else can. Some generate power under pressure. Others clean radioactive waste. One may even replace silicon entirely. And the most shocking part? The gemstone ranked number 1 is worth less than $100. Top 10 gemstones that could save the world. You've seen them in museums. You've walked past them in markets. But this time, look closer. Because if the future survives, these are the stones that made it possible. It doesn't glow in the dark. It doesn't shimmer in jewelry cases. But it could change how every building, satellite, and surface on Earth generates energy. Rank 10, Perovskite, the crystal that could replace solar silicon. At first glance, Perovskite doesn't look like something that could power the future. Found in fractured limestone veins across the Urals, the Italian Dolomites, and parts of Pakistan's Skardu Valley, the mineral appears almost muted, with a brownish, gray, or sometimes greenish cast. Most crystals form as imperfect cubes or rhombohedra, often less than a centimeter across. Nothing in its natural form screams beauty, and in archaeological digs, it's frequently mistaken for degraded feldspar. But that's the thing about perovskite. It's never been about what it looks like. It's about what it does. Named after Russian mineralogist Lev Perovsky in 1839, this calcium titanium oxide possesses one of the most promising internal structures in modern energy science, the perovskite lattice. Its unique arrangement of atoms allows it to absorb light more efficiently than silicon, the same silicon that defines our solar panels, microchips, and digital existence. Most natural perovskite is mined today not for jewelry, but for study. In China, Peru, and parts of Australia's Northern Territory, small-scale open-pit operations extract trace quantities for research and material engineering. The raw crystals, when used ornamentally, are brittle and difficult to polish. However, lab-grown versions with higher structural purity have begun to appear in collector markets. Faceted synthetic perovskites have sold for as low as $25 and as high as $300, depending on clarity and novelty, though they remain unstable in ambient moisture. As an archaeological material, it's irrelevant, but as a material with the potential to transform how humanity captures solar energy, it's at the center of every central clean tech lab on Earth. Some prototypes have achieved 25% solar efficiency in tests, rivaling the efficiency of the best silicon-based cells. Others are exploring its use in flexible panels that can coat windows, vehicles, or clothing. This isn't a dream, it's an arms race, and it starts with a humble, cube-faced crystal quietly waiting under the surface of the Earth. Some stones don't shimmer, they convert sunlight into electricity, quietly changing the way energy moves through the world. But not every gem that could save us lives under the sun. Some were forged for silence, radiation, and velocity, not on Earth's surface, but beyond it. It's not rare, it's not pretty, but inside this mineral lies an element so critical that it has been on nearly every NASA mission ever launched. Rank 9, Beryl, the element behind deep space tech. Not all gemstones are destined for jewelry. Some never leave the lab. Others never leave the atmosphere. Beryl is one of the most structurally versatile silicate minerals on Earth. Most people know it by its colored varieties, emerald, aquamarine, and heliodor. But when colorless or pale green, beryl becomes something else entirely. The primary ore for extracting beryllium, an element at the edge of known applications in aerospace, nuclear physics, and deep space communication. Chemically, beryl is a beryllium-aluminum cyclosilicate. Its hexagonal crystal system provides it with structural rigidity and minimal density, making it ideal for applications where weight and stability must be balanced under extreme conditions. But beryllium itself is toxic in raw form, requiring highly controlled extraction processes, a factor that has kept its use tightly regulated and geopolitically sensitive. In the post-war period, Beryllium became a quiet giant in the materials race. It lined the heat shields of early spacecraft. It forms key components in X-ray windows, particle accelerators, and precision optical systems aboard satellites. It does not corrode, it resists deformation at high speeds, and it dissipates heat better than aluminum. Most of the world's high-grade beryl comes from deposits in the United States, China, Brazil, and Madagascar. Mining is conducted through open pit or pegmatite tunneling operations, often yielding small, non-gem quality crystals buried in feldspar-rich matrices. These crystals, unremarkable in appearance, are rarely seen outside of industrial contexts. Yet each ton of ore can produce enough beryllium to build dozens of high-performance instruments used in telescopes, space probes, and even nuclear fusion prototypes. As a gemstone, facetted beryl can fetch thousands. As an industrial source, it's measured not in carats, but in survival. It isn't polished, it isn't worn. But without it, some of the most ambitious technologies we've ever launched would never have left the ground. Some minerals leave the earth to serve it, others never leave the ground, but protect everything on it. We launch beryllium into space to find the answers to our future. But right beneath our feet, a different kind of crystal works quietly, absorbing, neutralizing, filtering what we leave behind. It doesn't look high-tech. A shovel mines it. But to farmers, engineers, and environmental scientists, it's one of the most valuable tools in the fight to keep the planet livable. Rank 8, zeolite, the filter that cleans the earth. Not every gemstone dazzles. Some work quietly, not in jewelry cases, but in landfills, farm fields, and water plants. Zeolite is not a single mineral, but a group of hydrous aluminosilicates formed when volcanic ash reacts with alkaline groundwater. The result? A family of microporous crystals with one critical property. They absorb selectively, efficiently, and permanently. In scientific terms, zeolites act as molecular sieves. Their internal channels and cage-like structures trap specific ions while allowing others to pass. That's why they're used in some of the world's most overlooked yet essential systems, including municipal water treatment, nuclear waste remediation, industrial chemical separation, and even agricultural soil conditioning. Naturally occurring zeolites are mined in the US, Turkey, Cuba, and Japan. They are extracted by open-pit methods, then crushed, processed, and categorized by pore size and absorption capacity. Most raw zeolite looks like chalky gravel, but its function is anything but ordinary. During the 1986 Chernobyl disaster, thousands of tons of powdered zeolite were deployed to absorb radioactive cesium and strontium from soil and animal feed. In Japan, zeolite was airdropped by helicopter into contaminated groundwater after the Fukushima reactor breach. In both cases, it wasn't symbolic, it was structural, a mineral response to catastrophe. Today, the agricultural use of zeolite is expanding rapidly. In dry regions, it's blended into the soil to retain moisture and nutrients. In aquaculture, it's placed in water to reduce ammonia. In landfills, it's mixed into liners to capture leachate toxins before they reach groundwater. These are not dreams of future application. They are present tense deployments. Despite its wide use, zeolite remains commercially inexpensive, less than $200 per ton in bulk, but priceless in terms of what it removes: heavy metals, nitrogen waste, industrial runoff. The mineral doesn't fix the earth. It gives it more time. It doesn't shine, it doesn't sell. But without it, what we leave behind stays with us. Some minerals remove toxins from the earth. Others make it possible to move without adding more. Cleaning is one part of survival, but powering what comes next, without burning what came before, is the more complex challenge. One element has quietly powered phones, satellites, and even electric cars. But what's coming next goes far beyond lithium. Rank 7, graphite, the core of future batteries. It's not lithium that stores the charge. It's what holds the lithium. Graphite, a form of carbon with a hexagonal crystalline structure, is the single most essential material in the global battery economy. Without it, there is no EV, no portable electronics, no energy storage revolution. Naturally occurring graphite forms in metamorphic rocks, often in flake or amorphous form. Significant deposits are found in China, Mozambique, Brazil, and Canada, where the mineral is extracted through both open pit and underground mining. It appears matte, greasy, soft, industrial, not decorative, but its internal structure is anything but basic. Graphite's atomic arrangement allows it to conduct electricity, absorb ions, and resist high temperatures simultaneously. That's why it's used as the anode in almost every lithium-ion battery produced today. One standard EV battery contains up to 70 kilograms of processed graphite. More than lithium, more than cobalt. Demand is rising exponentially. Global electrification targets, from urban buses to national grids, have transformed graphite from a lubricant and pencil material into a strategic resource. In 2023, the U.S. Geological Survey reclassified natural graphite as a critical mineral, citing supply chain risk and processing limitations. Synthetic graphite exists, but its production is expensive, energy-intensive, and environmentally damaging. Natural graphite, when refined correctly, remains the most sustainable and scalable anode material known, and it's already shaping the future of solid-state and sodium-ion batteries. Commercially, graphite sells for as little as $800 per ton in its unprocessed form and over $10,000 per ton when coated for battery-grade use. It doesn't sparkle, but it drives everything, from last-mile delivery scooters to orbital drones. It doesn't store power, it makes storage possible. And in a world racing to unplug from the past, it's graphite, not gold, that gets us there. Every battery needs a core. Every circuit has a conductor. But beyond the devices we carry, some systems don't just run power, they contain it. In cooling towers, fusion chambers, and nuclear reactors. One mineral remains critical, not for energy output, but for control, shielding, and balance. It doesn't charge anything, but without it, much of clean energy science would collapse. Rank 6, fluorite, the invisible backbone of clean energy. Most minerals associated with energy are used to produce motion. This one stops them, precisely. Fluorite, also known as fluorspar, is a mineral composed of calcium fluoride. It forms in hydrothermal veins and sedimentary deposits, ranging in color from translucent green and purple to colorless. It may look like ornamental quartz, but its function is industrial and essential. Fluorite's most valuable role lies not in its appearance, but in what it releases: fluorine gas. Through a refining process called hydrofluoric acid production, fluorite becomes the cornerstone of technologies that demand absolute control in temperature, reactivity, and radiation containment. In clean energy systems, fluorite derivatives are utilized to produce low-friction, chemically inert materials, ranging from coolant circuits in nuclear reactors to specialized polymers in solar panel coatings and hydrogen fuel cells. It's also critical in the creation of aluminum, uranium enrichment, and even fluoride-based molten salt reactors, a class of next-generation nuclear systems that aim to generate power with near-zero meltdown risk. China currently dominates global fluorite mining, followed by Mexico, Mongolia, and South Africa. The mineral is extracted through both shaft and open pit operations. In its raw form, fluorite has a Mohs hardness of 4, which is soft, cleavable, and unsuitable for high-wear applications. Yet its role behind the scenes makes it one of the most geopolitically monitored, non-metallic minerals on Earth. During the push toward net zero, engineers and energy planners aren't asking how to generate power. They're asking how to stabilize, shield, and scale it safely. Fluorite isn't in the headlines, but it's written into the infrastructure. Market prices range from $300 to $600 per ton, depending on grade. Its transparent varieties are cut for collectors, but the real value lies in their structural integrity, not their visual appeal. It doesn't create energy. It makes clean energy possible. And in a world that must learn to contain its momentum, it holds the line. Stability, containment, control. That's what fluorite offers. Not as a source of power, but as the framework around it. But what happens when the framework itself becomes the limit? Not all materials were left behind because they failed. Some were buried because they worked too well for comfort. Deep in the mineral history of China, Spain, and Mesoamerica lies a red crystal once revered, then restricted, not for what it symbolized, but for what it could conduct. Rank 5. Cinnabar, the forgotten path to non-silicon chips. Before it was banned, it was everywhere. Cinnabar, also known as mercury sulfide, is one of the oldest pigments used by human civilizations. From imperial tombs in China to sacred murals in Mesoamerica, its deep crimson hue symbolized power, eternity, and sometimes death. But beneath the color was something more volatile. Cinnabar is the primary ore of mercury. When heated, it releases elemental mercury vapor, a toxic, unstable, yet highly conductive substance. In ancient alchemical traditions, it was seen as a paradox, solid yet fluid, fixed yet transformative. That symbolism wasn't superstition, it was science, centuries ahead of its time. During the mid-20th century, researchers in signal conversion and photonic switching began revisiting mercury compounds, including highly purified cinnabar, as potential substrates for non-silicon microelectronics. Under controlled conditions, cinnabar demonstrated semiconductor behavior capable of rapid signal modulation in optoelectronic environments. Its crystalline structure, trigonal, layered, and naturally stable under low heat, gave it properties attractive for early optical isolator prototypes. Some researchers proposed using cinnabar-based materials in pressure-sensitive switching, terahertz modulation, and infrared quantum detectors. But the toxicity of mercury halted all momentum. No commercial devices were produced. No patents followed. The idea vanished under layers of bureaucratic red tape. Today, cinnabar is tightly controlled under environmental safety protocols. Mining is limited to a few locations in Spain, Kyrgyzstan, and Peru. Its use is mainly restricted to historical preservation and strictly supervised geological sampling. Even in mineral markets, raw cinnabar with a purity above a certain level is banned from open trade. But behind closed lab doors, interest is reawakening. Not in cinnabar itself, but in the structural analogs it inspired, safer compounds modeled on its lattice, promising lower energy consumption and higher optical responsiveness than silicon. In a world desperate for new chip architectures beyond the silicon wall, cinnabar's legacy is no longer symbolic. It's foundational. It poisoned. It preserved. And for a brief moment in scientific history, it almost powered the future. Some materials couldn't be trusted. Too unstable, too toxic, too unknown. Others didn't ask to be trusted. They worked, quietly, reliably, at scale. For decades, one mineral has underpinned the entire digital architecture of our world. From the devices we touch to the signals we never see. It's not rare. It's not beautiful. But it's everywhere. Rank 4. Silicon quartz, the foundation of the digital world. It doesn't store energy. It doesn't filter toxins. It doesn't glow. But it's inside every device you've ever used. Silicon quartz, not the mineral we admire for beauty, but the one we demand for precision. A colorless, high-purity form of quartz, silicon dioxide, that forms the starting point for the most essential material of the modern era, semiconductive silicon. In its raw form, quartz is one of Earth's most abundant minerals, but only a tiny fraction meets the chemical and structural standards required to be turned into the silicon used in microchips, solar cells, and sensors. That level of quartz is found in specific geological environments, such as pegmatite veins and hydrothermal pockets, with notable deposits in the United States, Brazil, and Norway. Once extracted, the quartz is refined into metallurgical-grade silicon, which is then purified again through the Siemens process to become electronic-grade silicon, the ultra-thin wafers that underpin modern civilization. There is no smartphone without it, no satellite, no AI, no electric grid. The crystal structure of silicon quartz allows it to be both insulating and semiconducting, a property that has driven every breakthrough in computing since the 1950s. And yet its importance has made it both strategic and vulnerable. Only a few countries dominate the high-purity quartz market, and even fewer control advanced processing. While synthetic quartz can be grown in autoclaves, demand for natural high-purity feedstock continues to rise. The raw price of quartz is low, often under $200 per ton, but by the time it becomes a 300 millimeter wafer inside a 5 nanometer processor, its value becomes incalculable. It doesn't innovate, it enables innovation. And without it, the digital world ends before it begins. Some minerals made the digital world possible, others hint at what may still be missing from it. For decades, we've engineered glass, metal, and silicon to transmit information. But deep in the deserts of California and Chile lies a crystal that did it, naturally. No copper, no laser, no coating, just light, carried through solid stone. Rank 3, Ulexite, the natural fiber optic. It doesn't conduct electricity, it doesn't store energy, it simply shows you what's underneath, as if the rock itself were made of glass. Ulexite is a sodium-calcium borate mineral, often referred to, unofficially, as TV rock. But unlike modern fiber optics, this crystal doesn't require engineering. Its unique internal structure naturally aligns into thousands of microscopic fibers, each acting like an individual light pipe. The result, an optical transmission system embedded in solid stone. Discovered in the 19th century and named after German chemist Georg Ludwig Ulex, Ulexite occurs in arid lake beds and borate-rich sedimentary basins. The most significant deposits are found in California's Mojave Desert, parts of Nevada, and northern Chile's Atacama region. It forms as soft, fibrous nodules, white, chalky, and almost weightless. But when cut and polished across the grain, it behaves like a primitive screen. In laboratory studies during the 1960s and 70s, Ulexite became a curiosity among physicists and materials scientists. Researchers noted that its natural ability to transmit two-dimensional images without distortion mimicked the behavior of bundled fiber optic cables. The mineral could project clear images from one surface to another with no artificial enhancement. Its fragility and moisture sensitivity ruled it out for industrial applications. But the underlying principle, internal optical coherence without artificial alignment, later influenced the design of synthetic fiber bundles and graded index lenses. More recently, Ulexite has gained attention as a model for bio-inspired photonic materials, not because it can be used directly, but because it demonstrates what nature did first: turn light into information without the need for electricity, silicon, or glass. Commercially, Ulexite is too soft for cutting, with a Mohs hardness of 2.5 and too water-soluble for widespread use. But in classrooms, geology kits, and materials labs, it serves as a physical reminder. Not all optical technology begins with engineering. It wasn't designed to carry light, but it did, and it still does. Some minerals reveal what lies beneath, bending light, displaying images, without wires or code. But others go further. They respond to heat, to pressure, to movement. And in a world demanding clean energy at more minor scales, one crystal may hold the key to power without combustion, even without a battery. Rank 2, Tourmaline, the voltage stone. Most crystals sit still. Tourmaline responds. Composed of a complex boron silicate structure with variable elements like iron, lithium, and magnesium, tourmaline is one of the only naturally occurring materials that exhibits both pyroelectric and piezoelectric properties. That means it generates voltage when exposed to heat and a different kind of voltage when pressure is applied. This dual responsiveness makes tourmaline unique, not for jewelry, but for energy systems that function on micromovements: vibration, compression, and temperature shifts. Black tourmaline, also known as squirrel, is the most common variety, found in pegmatites across Brazil, Africa, the United States, and Afghanistan. Its long, prismatic form and natural polarization allow it to accumulate surface charges at opposite ends of the crystal. In the 20th century, this behavior made tourmaline an object of study in both material science and early sensor design. In 2014, researchers at Sungkyunkwan University in South Korea demonstrated how aligned tourmaline nanorods could be used to harvest biomechanical energy, converting body motion into electricity to power small sensors. Subsequent studies explored tourmaline's integration into flexible electronics, nanogenerators, and wearable diagnostics. Unlike rare earth magnets or high-demand lithium, tourmaline is non-toxic, abundant, and recyclable. It can be ground to powder, embedded in polymers, or used in ceramic composites without requiring expensive smelting or chemical stabilization. Its efficiency isn't high yet, but its scalability is what makes it matter. In regions without stable power, piezoelectric systems offer a radical solution, harnessing energy from everyday activities such as walking, breathing, and even rainfall. And at the center of many of those early devices is tourmaline. Commercially, its gemstone varieties, such as indicolite, rubellite, and paraiba, can reach thousands per carat, but black tourmaline, the kind used in research, sells for under $50 per kilo. It's not valued for its looks. It's valued for what it does under stress. It doesn't store power, it creates it. From movement, from heat, from the smallest interactions. Not every source of power needs a plug. Some charge through movement, through heat, through friction, but power is only part of the story. What comes next is visibility, or rather, the lack of it. As devices shrink, disappear into surfaces, or merge with the body, the materials that carry current must do more than conduct. They must vanish. One mineral, once dismissed as too unstable for industry, it is now at the frontier of transparent circuitry. Rank 1. Zincite, the future of transparent electronics. In the 19th century, it was a byproduct of the furnace, discarded, unstable, and prone to fracture. Today, it's being reimagined, not as waste, but as a window. Zincite, a rare hexagonal crystalline form of zinc oxide, ZnO, occurs both naturally and synthetically. Its most vibrant forms, deep red to orange, typically form in the exhaust systems of zinc smelting operations, though natural specimens have been found in Poland, the US, and Namibia. For decades, it was studied for its color and luminescence, but its true significance lay beneath the surface. Literally. Zincite is a wide bandgap semiconductor, meaning it can conduct electricity in ultra-thin films while remaining optically transparent. Unlike traditional conductors like copper or silicon, zinc oxide transmits both light and charge, making it one of the few materials capable of supporting the emerging field of invisible electronics. Over the last 20 years, researchers have refined methods for depositing zinc oxide onto glass, polymers, and flexible substrates. It now forms the basis of transparent thin-film transistors, TFTs, UV detectors, touchscreens, bright windows, and display coatings. Unlike indium tin oxide, ITO, currently the dominant material in transparent electronics, ZnO is far more abundant, stable, and non-toxic. In 2021, a team at Osaka University developed ZnO-based transistors that are thinner than a human hair and can bend, flex, and maintain conductivity on transparent plastic. In the medical field, Zincite-derived sensors are being tested for skin-based health diagnostics, ocular interfaces, and neural mapping systems, devices that appear to be invisible on the surface but interact below it. As of 2025, transparent circuitry remains in early stages, but scaling is accelerating. Zincite, once overlooked by industry, now plays a crucial role in replacing rare, unsustainable materials in mass-market consumer technology. It bridges the visible and the invisible, not metaphorically, but materially. You can't see it. You don't wear it. But if electronics are to vanish into the world around us, Zincite is how they survive. Some gemstones shape circuits, others entire civilizations. If you found this journey through science and minerals meaningful, your support helps us keep going, to research deeper, film further, and tell stories no algorithm could predict. Because this is only part of the story. In the next chapter, we move beyond what is measurable, to the stones that shaped myth, ritual, and fear. Gemstones once believed to hold supernatural powers. and in some cases, still protected by law, tradition, or silence. Rare gemstones with supernatural powers. Mythical gemstones found in history. Subscribe if you want to be part of it. Like, if you want us to go further. And until then, keep asking what the stones are still trying to tell us.